Some plants are already resistant to drought. Just they are not our crops, but they are there. The genes are there. If we just put them in the plant that we eat, so we can eat them every year, why should we stop?
Genetically modified crops are heavily regulated in Europe, to the point that plants that are legal in most other countries are illegal in the European Union. Today we want to look into the different methods of plant breeding that are used in agriculture and compare their impact on the genome. I'm Dennis Eckmeyer, your host, and you're listening to episode 11 of the Science for Societal Progress podcast.
I'm Hélène Pidon. I'm a French postdoc in a German institute in crop science.
Hélène searches for genes that give wild plants a resistance to disease. She wants to use these genes to make barley plants resistant as well, reducing the need for pesticides. But let's start at the beginning. I wanted to know what the original breeding process was like before we had scientific knowledge to apply to crop development, and especially what the impact of this practice would be on the genes.
So basically, we are now at the beginning of agriculture. At first, it was just taking the plant that was the best looking and just sowing the seeds for the next generation. So it was kind of empirical at the beginning, and most of the plants have evolved that way, driven by humans choosing the plant they want for the next generation. And the plants that we are now eating are not at all the plants that were there at the beginning, that were there before humans. And they will not survive in the wild because they are not adapted. They are adapted to agriculture and not to nature.
What happens to genes if you do this artificial selection?
When you know about natural selection, the plant that is the best adapted to its environment will have offspring that will better survive. And so their gene will continue in the generation. And with agriculture, it's not driven by adaptation to the environment. It's driven by the adaptation of what human wants. Even by just choosing the parents that were the best for us, we were already applying selection on genes. We were already selecting traits, selecting even mutations that were naturally occurring. And then these mutations were the one that survive now in the plants. That they were not there at the beginning. They appear and just in one plant that will not have offspring and disappear because it was not adapted. But we made this mutation survive to the next generation and now be all over our fields. The plant that we have now were species that didn't exist before humans.
Is that just one gene that changes?
It's everywhere in the genome. It's not even quantifiable. When you look at wheat has 3 genomes. That means that at some point, the genetic material was doubled and then tripled. Humans are diploid, and for one chromosome there is a pair, and for them there is 3 pairs. So this was also something that was driven by humans, because with these 3 pairs of chromosomes, so these 3 copies of gene everywhere, selection can be much faster, and we have stuff that are much better with better yield, because everything is related to yield, how many plants you can retrieve for your consumption.
But we don't really have control over what we're doing, right?
Yeah, definitely. It just, oh, this one looks good, I will take this one, and not even knowing what's happening in the genome and not questioning ourselves. Is it affecting the natural environment? Because just by making agriculture, we change completely the environment. And it's already completely synthetic compared to before agriculture.
Okay, so for millennia we selectively bred crops to produce higher yields, and in the process introduced enormous changes to the genomes of these plants, without even knowing that we were doing it, and with no regard for the environmental consequences. And the resulting plants are fully domesticated and unable to survive without human attendance. Then the so-called Green Revolution happened.
Around the 20th century, there was a big change in the way agriculture was done. So we moved from farmers doing all the work of selecting their crops and trying to get the best yield possible with putting cow poop on their crops and stuff like that. To something much more industrialized, because there were less and less farmers and more fields and a big need of food. And so more and more things that were previously done by the farmers were moved to companies. There was, in fact, something that farmers were asking for. They were asking for expertise outside and giving this work to someone else. So the big change was adding pesticides to the crops that allow to have better yield, but also having companies that select plants, that make the plant breeding. At this point, science enter into breeding, not just, oh, this one is looking good, so it will be for next year. But, oh, this one is looking good, and if I cross it with this one, it's looking also good. And there we are still at something very phenotypic, very based on the traits and what we can see of the plants. Like just, if I'm crossing those two, I have a better yield, I have a better resistance, so I will choose this one. But still not really knowing what's happening on the gene part. And there was also, we know that DNA exists, and we know that mutation are all the things that can create new traits, new resistance, new better yield. So how can we increase the number of genes that are interesting for us, the number of mutation interesting for us? And so at this point, we have some stuff that are pretty random, like putting a nuclear source in the middle of a field, just waiting for mutation to appear in plants. And yeah, some will be looking good, and so we will take them.
Wait, say that again. They were putting radioactive material into the field?
Yeah.
To see what happens?
A radioactive source in the middle of a field. And I'm talking about Europe, and not so long ago.
So when was that? That was 1900 and...
I think 1970s. It was still ongoing, even maybe later.
1970s. That was already the time where people started to become environmentally conscious, right?
Yeah. But, I mean, at some point, we are just changing the DNA. But we were not knowing at all what we were doing. And there is also a technique that enters, so chemical mutagens too, like EMS, so it's one of the most used chemical mutagen. Basically, you take a plant and you put it directly it's a liquid, basically. You put it into the liquid, and then there will be a lot of mutation in the seeds at the next generation, and you will select from that. Because you make new mutation, you induce a lot of mutation, and then some traits may be better afterwards. You can have gain some resistance, you can have a bit of more yield, or a bit of a tolerance to salinity, or I don't know which trait. When you put it into the liquid, you don't know what you will get. And you don't even know what's happening in the genome.
So with the Green Revolution, we had companies entering agriculture, and they developed pesticides and fertilizers to increase crop yield. They also began implementing targeted crossings to get a good trait they discovered in one variety into the plant that is currently the best they had for production on the fields, the so-called elite crop or elite material. And they also figured that by inducing random mutations at a higher rate, using radiation and chemical mutagens, they could create new varieties to select from much faster. And it turns out, by using mutagenesis on our elite plants directly, many complications that come with crossbreeding can be avoided.
So you have a plant which is wild and has a lot of things you don't want. Usually it's very low yield, it's very bad looking, but there's something like a resistance to a disease or a better resistance to drought, for example. And so then this plant, you will try to cross it with your elite material, the one which is already in the field. And at this moment, you have something which is still bad looking. It's a bit less bad looking than the previous one, but it's bad looking. And you just retrieve the offspring that are resistant, for example, the one that have the trait that you want, and then cross it again with some elite material. And so each time that you cross it with an elite material, you get rid of a bit of the wild part that you don't want, and try to select each time for the one that are the most elite, but still with a trait that was interesting you in the wild in the beginning. And so each time you have a generation, and a generation is a year, basically. So you need at least 10 years to make a new variety. It's so difficult to take a trait from a wild plant. It's much more easy to create it by mutation, finally. Even if mutation is random, it's still kind of easier because you make this mutation appear directly into your elite material. And it's not coming with non-wanted traits. It's coming directly. But you are playing a bit with the dice, like, will it appear or not? But the idea was always to try to go over this fact that when you cross with a wild, you have a lot of things that are coming that you don't want. And also the fact that more and more, as I was saying, the wild plants don't really exist anymore, or it's another species, and sometimes it's very difficult just to make the cross. Just to make the cross, then it's sterile or stuff like that. So basically, that's why mutagenesis is so used. Finally, the trait you want will appear in the plant, in the background of the plant that you want.
And now we enter the era in which we begin to really understand the genetics.
With new techniques, we can directly see what gene is responsible for what trait. It's easier to follow from generation to generation if your trait is still there. But also, you can directly put the mutation of the gene you want in the plant, knowing exactly what you're doing compared to doing it completely random. It's also allowing you, so for example,
Let me explain a few terms. There's transgenesis, which is the process of introducing foreign genetic material into host cells. Basically, a whole gene is introduced into the genome. Gene editing, on the other hand, means that you are altering just a few letters in the code to change a gene from one variety to the other. These methods allow us to introduce naturally existing gene variants with beneficial characteristics into our plants without the difficulties that we face when trying to introduce the gene through crossbreeding. And they eliminate the unpredictability of all prior methods. In Helene's case, she wants to make barley resistant to disease. And when we find a gene that makes a different plant resistant to a disease,
we can introduce this kind of disease resistance. And if we have disease resistance already at the genetic level in the plant, that means that the plant is able to defend itself against the disease without applying any pesticide to it, just by changing a few bases in the DNA precisely where we know it will be useful.
So what you're saying is that actually the actual change that you're inducing using gene editing methods like CRISPR are actually much smaller than what you would do when you would use more traditional methods?
Yeah, with CRISPR, we can even change just one base, meaning just one letter. And just to give you an idea, the genome of wheat is 10 power 10 letters. It's huge, and we are just changing one letter. Whereas when we are putting mutagenesis, we are applying some mutagenesis, it will be tens, hundreds of mutations occurring in the same time, where we don't know where, basically, everywhere in the genome.
10 to the power of 10? It's a 10 and then 9 zeros. That's 10 billion. So you only change 1 in 10 billion instead of hundreds in 10 billion. Both doesn't seem like a lot.
It will really depend on the kind of mutagenesis you can have, but it can be more. But it's a single event. It's like doing it one time. And there's also natural occurring mutation. In wheat, we consider that there is 100 mutation every billion base pair in one generation. If you consider just a 1 hectare field, then you can have 20 billion mutation in just one field. It's more than the total size of the genome. So there is hotspot of mutation naturally occurring, but in a 1 hectare field, there will be already a lot of mutation even if we do nothing. And we can't check every field for just the mutation we want. It's not possible.
Okay. So we already have a lot of high mutation rate naturally. And then we use gene editing, which is low, but it's very targeted. So, I mean, you do it to have an effect. So you put you change the genes that count, that make a difference, and it's targeted. How well do we know what happens when we use CRISPR? Because there was this study that everybody's talking about that CRISPR actually is not as precise and specific as we thought it to be in the beginning, but how precise is it really? How many unintended changes do we make, and how does that compare to earlier methods, to the mutagenic methods?
It's still quite controversial, this study. The change that we don't mean to do with CRISPR are called off-target effects. It seems that it's really, really, really low, like sometimes it will happen once in the genome. The problem is when we do what we call largely a genetically modified plant, so it's CRISPR or the older methods of transformation, you always go through an in vitro phase. To introduce a mutation in a plant, you usually do it in what we call culls that are indifferentiate tissue of plant that we induce. And then we make these cells that we change into a plant again. This is quite stressful for the plants. There's a lot of things that are going on during this phase, and that can induce also some mutation that we don't know where they happen. But it's something much less than what mutagenesis with EMS or something like that will do. But we know that this can induce also mutations. And mostly it seemed that the thing that was thought to be off target of CRISPR were mostly induced by this regeneration.
And this technique is not specific to gene modification methods.
In the modern process of plant breeding, even without genetic transformation, you go often through this phase of in vitro culture. It's basically everywhere in breeding.
In Europe, genetic modification is strongly regulated. The European Court of Justice now ruled on the status of plants modified through gene editing. It ruled that gene-edited plants must go through the same difficult approval process as plants that have been modified through transgenesis.
In their definition, the GM is a way to change a plant that may have not occurred naturally. And basically, afterward, they just say, are excluded of these plants obtained by mutagenesis. Because we have enough knowledge about it, because it's been so long that we are using it, that we know that it's not dangerous. So they are saying basically that mutagenesis is a form of genetical modification, which is true because each time that you are crossing a plant, you are making a genetic modification. But yeah, they are just saying that this one will be excluded because we know there is no harm going from that, because every plant you eat have been mutagenized at some point, even in organic farming, and there is no, in big crops at least, there is no plants that have not been at some point subject to some kind of mutagenesis, artificial human mutagenesis. So if you forbid the use, basically you can't use the crop that have been produced for like the last 50 or 60 years, and you go back to something which is very low producing and susceptible to diseases and stuff that no one wants. Organic farmers don't want it either, because the variety they have are all like that. And if we suppress the possibility to use mutagenized crops, then we go back 60 years in the past, which is a very big difference for the crops.
Okay, so to sum up the situation, we basically have three ways to perform gene modification here.
So we have mutagenesis, where you're changing stuff in the genome without knowing what you are doing. You're just trusting that at some point maybe something interesting will appear. The second stuff is the GM on the market, not in Europe, but basically the rest of the world. Transgenesis, so basically you are taking a gene. So we can take it obviously for another species, and that's what have been done mostly, for example, with the BET genes, which are resistant to insects. But you are not forced to take it from bacteria. You can take it from just a sister plant. or from another plant which is already there. And gene editing is just changing precisely one or two base, so two letters in the DNA, to make a change that you know will occur because you have some other studies, scientific studies that say this gene is doing that, and if you change that, it will do that very precisely.
And the Court of Justice ruled that mutagenesis, the most random and unpredictable of these approaches, has proven to be safe enough, whereas the methods that we know are much less invasive could not be considered safe. This I find mind-blowing. If mutagenesis is safe, and I agree that it has proven to be, then how can they determine that the other methods weren't safe?
But if we say there's a traditional method that has a lot of randomness in it, and say, well, that is safe, then how can we justify saying the others that are much less random are not safe?
The one where we are directly applying what we want, much more recent, and the general public was more aware of what was going on at this point and was maybe not aware of what was going on before. And they don't understand everything like everyone. It's normal. They become afraid. I think it's kind of also a dogma. When we were not knowing what we were doing, it was like finally just kind of a natural thing that we make faster. But now that we know what we do, I think people are saying that now we are changing stuff in a way we want, so we are playing God, let's say. Whereas when we just do something random, it's random. But finally, isn't it better to have control on what we do than just make random stuff saying it's not completely our fault if it's happening?
What are the crops that Europeans fight against but other countries embrace? One type that Hélène wants to tell us about are the so-called BT plants that she had mentioned before briefly as an example for transgenesis.
So what's a BT crop? A BT crop is a crop which has a gene from a bacteria that is in fact an insecticide.
And the BT stands for the name of the bacterium, right?
Yeah. The BT stands for Bacillium thuringiensis, and this bacteria is in fact used in field directly. So in organic farming, you can take a bit of the bacteria and put the bacteria directly in your field. The difference is that we don't want the plant to do the same thing as the bacteria is doing by itself. We can put the bacteria, it's natural in an organic field, but having the gene directly in the plant is not seen as correct. Moreover, people are saying, yeah, but it's plants that are producing an insecticide in continuous, it's dangerous for the environment. But this insecticide is a protein, so it's basically the same thing we are made of. It's amino acids all together. It's something which is very fast degraded in nature, and that basically is made of the brick of living. It's not a synthetic chemical in the way we are seeing other pesticides. It's not something that will remain in the soil or something like that. It has a very low life. And moreover, it's very precise. Like there is in fact not one BT protein, but a lot. And those proteins are targeting precisely one or two insects, and not the whole insect community, it's just one or two insects. So it's a very low range of action compared to what can be synthesis insecticide, for example, or kind of insecticide that can be used in organic crop also.
So that we have this bacterium, and it produces an insecticide, and we can put the same gene into the plant, but if we put it into the plant, that's wrong. And if we leave it in the bacterium and put the bacterium on the field, that's fine. So, and you say that these proteins are very specific. How do we know that?
There is a lot of tests that are done on insects, on humans, on animals. There is a lot of studies done. And none of them have proved any adverse effects to humans of these BT proteins. And those beefy proteins are obviously tested around a large set of insects before we can say this one is specific to this insect or this one. So yeah, there's a lot of tests before we release a GM crop. It's even more difficult right now to release a GM even in countries where it's authorized than to release a human drug. But that means that there is like 8 years of work to test the effect that the plant can have on humans, on the environment. But the thing is, as companies are doing these tests mostly, even if it's checked afterward by some authorities, people are not trusting it because, yeah, it's a company that makes the test. But companies have no interest in selling something that is not good because it will appear at some time. And they don't want to sell just for 2, 3, 4 years. They want to sell forever.
No conversation about GMOs would be complete without glyphosate. Glyphosate itself has nothing to do with the methods of gene modification. It is an all-round herbicide that kills all plants. In farming, it is useful to get rid of unwanted weeds. Genetic modification only came into play when Monsanto created glyphosate-resistant crops. This allows the use of glyphosate even after the seeds are sowed and while the crops are growing on the fields, because it can't harm the crop anymore. What does Hélène think of this approach?
For me, the resistance to glyphosate is not a good thing. It's something that was done also because some farmers were wanting it because it's easier. But it's not something very interesting that we can do. And what was particularly interesting for Monsanto and the resistance to glyphosate thing is that glyphosate at this time was their own product. And no one else was able to sell it because it was under patent. So they were selling like a package. The GM was not the thing that was giving them so much money. The thing that allowed them to earn so much money was selling the glyphosate with it. Does a company have any interest in selling something normally that will stop the farmers from using pesticide? If they are the ones selling the pesticide, no.
So private interest of companies can inhibit progress towards more efficient, environmentally friendly, and nutritionally improved crops. But what about the public sector?
It's so difficult to put a GM on the market now that only big companies can do that. If it was a bit less difficult, then some public institution or what can also produce some GMs that can be not only for commercial reasons, but also for more practical reasons, like improving resistance to pests, and so you don't spray chemicals, improving resistance to drought, improving resistance to anything, having a higher yield with lower chemicals, either natural chemicals or synthetic ones. With also the global warming coming, the environment is changing really, really fast. And breeding has struggled to cope with that and follow the rhythm of global warming. Global warming is right now coming faster than normal breeding can do. But with GM, we can go faster. And we can manage to get more environment resilience for crops and prevent starvation caused by loss of yield. Like right now in Germany, there was a huge drought, and I think they have 40% less of wheat than the other years. The public sector and the academia, they are the ones that are able to release this kind of genes on the market. The public sector would like also to release some GMs. There's this example of the golden rice for Asia, which is still in the pipe for such a long time, and which at the beginning was owned by companies, but companies saw that they had not so much commercial interest in selling this thing. It's a rice which has high vitamin A content and can improve nutrition in poor countries where rice is a staple crop. So companies realized that it was so hard to manage to get this really high vitamin A content and not very commercially advantageous. And so they let the public sector do it. And right now, I think they are quite close to release the golden rice in the market.
One GMO success story came from a public-private partnership. between a scientist at Cornell University in the USA who developed the GMO and a company that made it commercially available.
A big virus outbreak happened in Hawaii, and almost all papaya were dying of that. And the solution came from GM, from a resistant gene that was put into the papaya there. And almost all the trees in Hawaii now producing papayas are GM plants that resist to this virus. And without this gene and without this GM papaya, there would be no more papaya in Hawaii now, which is also kind of important for the farmer over there because it was one of the major production.
And what method was used to create the papaya?
So it's not gene editing, it's transgenics, the previous methods. For the moment, as far as I know, there is no gene edited plants that are authorized anywhere.
And finally, if we want to be ecologically friendly, isn't organic farming the way to go?
For me, organic farming is not a good way to go ecologic. It's based on something which is absolutely not scientific, which is that what's coming from nature is better than what we can do. And the varieties they are using are the same that are used in conventional farming. But if your plant can't defend itself, then you need to put some pesticide on a field. Organic farming is using pesticides that are called natural because they are mineral or bacteria, things that you can't find in the nature. You don't synthesize them. And if you don't have even the synthetic and efficient one, then you will use the natural one, which are not better for wildlife, but less efficient. So you will need to put even more. The most used things are copper and sulfur, and they are shown to be very dangerous to the environment, to the soil life, to the insects, but they are used, and every year the European Union is saying, yeah, you can continue using it. For me, GM is the best future that can happen to organic farming, because if the plant can defend itself, you don't need pesticide anymore.
And with this we end this episode. Thank you very much for listening. Please don't forget to visit our website scienceforprogress.eu or follow us on social media at Sci4Progress on Twitter, Facebook or Instagram. And please consider to become a member on our Patreon account, patreon.com/Sci4Progress. Have a nice day.